Fluid conditioning is critical in maintaining proper operation of a hydraulic system. In this course, you will learn about different types of filters, their location, and how they keep hydraulic fluid clean. You'll also learn about the importance of regulating the temperature of hydraulic fluid with devices like heat exchangers. For example, fluid that is too hot or too cold can have a negative impact on system performance.
Cleanliness of hydraulic fluid has become critical in the design and operation of fluid power components. With pumps and valves designed to closer tolerances and finer finishes, fluid systems operate at ever-increasing pressures and efficiencies. These components will perform as designed as long as the fluid is clean. Oil cleanliness results in increased system reliability and reduced maintenance.
As particles are induced or ingressed into a hydraulic system, they are often ground into thousands of fine particles.
These tiny particles are tightly packed between valve spools and their bores, causing the valve to stick. This is known as silting. To prevent silting, early component wear, and eventual system failure, engineered filtration is required. Engineered filtration includes understanding required micron rating, application of the beta ratio, maintaining proper ISO code cleanliness levels, filter location specific to the system design and environment. Micron is the designation used to describe particle sizes or clearances in hydraulic components. A micron is equal to 39 millionths of an inch. To put this into perspective, the smallest dot that can be seen by the naked eye is 40 micron. Consider the following illustration. If we looked at a human hair magnified 100 times, the particles you see next to the hair is about 10 micron. Industrial hydraulic systems usually filter in the 10 micron range. This means that filters are filtering particles that cannot be seen by the naked eye. Filtration devices are used to filter particles out of the system's fluid. A filter's efficiency is rated with a beta ratio. The beta ratio is the number of particles upstream from the filter that are larger than the filter's micron rating, divided by the number of particles downstream larger than the filter's micron rating. In this example, there are 200 particles upstream which are larger than 3 microns. These flow up to and through the filters. A filter that allows more particles through, or in other words, one that is less efficient, has a low beta ratio. You can see that the filter at the top allowed 100 particles through. The filter on the bottom allowed only 1 particle through. If we apply these numbers to the beta ratio formula, we can see that the filter at the top has a lower or less efficient beta ratio, and the filter at the bottom has a higher or more efficient beta ratio.
To specify the cleanliness level of a given volume of fluid, we refer to what is known as an ISO code or ISO solid contamination code. This code, which applies to all types of fluid, provides a universal expression of relative cleanliness between suppliers and users of hydraulic fluid. Based on a milliliter of fluid, a particle count is analyzed using specific sizes of particles, 4 micron, 6 micron, and 14 micron. These 3 sizes were selected because it gives an accurate assessment of the amount of silt from 4 micron particles and 6 micron particles, while the number of particles above 14 micron reflect the amount of wear-type particles in the fluid. To interpret the meaning of these results, a graph like the one shown would have been consulted. In this example, a rating of 22, 18, 13 indicates the following. The first number, 22, indicates that the number of particles greater than or equal to 4 micron in size is more than 20,000 and less than or equal to 40,000 per milliliter. The second number, 18, indicates that the number of particles greater than or equal to 6 micron in size is more than 1,300 and less than or equal to 2,500 per milliliter. The third number, 13, indicates the number of particles greater than or equal to 14 micron in size is more than 40 or less than or equal to 80 per milliliter. This ISO code is meaningful only if we can relate it to the required cleanliness level of our hydraulic system. This is usually based on a manufacturer's requirement for cleanliness levels in which a component may operate. For example, most servo valves require an ISO code of 15-13-12 or better, while gear pumps may operate adequately in fluids with 18-16-15 ISO. Filter placement is critical for maintaining acceptable fluid cleanliness levels.
adequate component protection, and reducing machine downtime.
Filter breathers are critical in prevention of airborne particulate ingression.
As the system operates, the fluid level in the reservoir changes. This draws in outside air, and with it, airborne particulates. The breather filters the air entering the reservoir. Pressure filters are often required to protect the component immediately downstream of the filter, such as a sensitive servo valve, from accelerated wear, silting, or sticking. Pressure filters must be able to withstand the operating pressure of the system, as well as any pump pulsations. Return filters best provide for maintaining total system cleanliness depending on their micron rating. They can trap very small particles before they return to the reservoir. They must be sized to handle the full return flow from the system. A kidney loop or offline filtration is often required when fluid circulation through a return filter is minimum. Being independent of the main hydraulic system, offline filters can be placed where they are most convenient to service or change. Offline filtration normally runs continually. In this learning lab, you will learn the proper placement of filters. A description explaining a filter's placement will appear at the right side of your screen. Click and drag the description to the proper filter area. Temperature control is critical in hydraulic systems. Even with the best circuit design, there are always power losses in converting mechanical energy into fluid power. Heat is generated whenever fluid flows from high to low pressure without producing mechanical work. Heat exchangers may be required when operating temperatures are critical or when the system cannot dissipate all the heat that is generated. There are two basic types of heat exchangers. Each is based on a different cooling medium: water-cooled heat exchangers and air-cooled heat exchangers. If cooling water is available, a shell and tube heat exchanger may be preferred. Cooling water is circulated through a bundle of bronze tubes from one end cap to the other. Hydraulic fluid is circulated through the unit and around the tubes containing the water. The heat is removed from the hydraulic fluid by the water. There are advantages to this type of cooler. They are the least expensive, they are very compact, they do not make noise, they provide consistent heat removal year-round, and they are good in dirty environments. The disadvantages are, water costs can be expensive. With rupture, oil and water may mix, and usually require regular maintenance from mineral buildup. Air-cooled heat exchangers consist of a steel radiator core through which oil flows while a strong blast of air passes across the core. In industrial applications, the air is pushed by an electric motor-driven fan. The advantages of this type of air-cooled heat exchanger are, they eliminate problems associated with cooling water, they have low installed costs, and the dissipated heat can be reclaimed. The disadvantages are, there is a higher installation cost, noise levels range from 60 to 90 decibels, and they are larger in size than comparable water-cooled equipment. In addition to holding the system fluid supply, the reservoir serves several other important functions. It cools the hydraulic fluid. This is accomplished by dissipating excess heat through its walls. It conditions the fluid. As oil waits to leave the reservoir, solid contaminants settle, while entrained air rises and escapes. The reservoir may provide mounting support for the pump or other components. A well-designed hydraulic system always includes a properly designed reservoir. An industrial reservoir should include the following components: a baffle plate to prevent returning fluid from entering the pump inlet, a cleanout cover for maintenance access, a filter breather assembly to allow air exchange, a filler opening well protected from contaminant ingression, a level indicator allowing upper and lower levels of fluid to be monitored, and adequate connections and fittings for suction lines, return lines, and drain lines. It is often stated that the hydraulic fluid is the heart of the system, or the most important component. The reservoir serves a critical role in maintaining the efficiency of fluid transfer and conditioning.
This course has been designed to help you understand how different check valves function and the strategy of where they are used in the system. Check valves are a simple but important part of a hydraulic system. Simply stated, these valves are used to maintain the direction that fluid flows through a system. And since check valves are zero leakage devices, we can use them to lock hydraulic fluid from the cylinders.
Inline check valves are classified as directional control valves because they dictate the direction flow can travel in a portion of the circuit. Because of their sealing capability, many designs are considered to have zero leakage. The simplest check valve allows free flow in one direction and blocks flow from the opposite direction. This style of check valve is used when flow needs to bypass a pressure valve during return flow, as a bypass around a filter when a filter becomes clogged, or to keep flow from entering a portion of a circuit at an undesirable time. Because of slight spool leakage on standard directional control valves, we must add a check valve to the circuit if we need to hydraulically lock a cylinder. This type of check valve is referred to as a pilot-operated check valve. Unlike a simple check valve, reverse flow is required through the valve to retract the cylinder. This is accomplished by allowing pilot pressure to act on a pilot piston, thus opening the check valve and retracting the cylinder. To extend the cylinder, the check valve allows fluid to flow freely in one direction and blocks flow in the opposite direction. In this learning lab, you will learn
In this course, you will be given an overview of several accessory components that are used in most hydraulic systems. You'll learn about accumulators, pressure switches, gauges, flow meters, and manifolds. These components are vital to proper system operation, and understanding how they are used in a system is an important part of this basic hydraulic course.
Accumulators are devices that store energy in the form of fluid under pressure. Because of their ability to store excess energy and release it when needed, accumulators are useful tools for improving hydraulic efficiency. Industrial hydraulic accumulators are typically classified as hydropneumatic. This type of accumulator applies a force to a liquid by using compressed gas. The two most common types of hydropneumatic accumulators are the bladder-type accumulator and the piston accumulator. The name of each type indicates the device separating gas from liquid. A hydropneumatic accumulator has a fluid compartment and a gas compartment with a gas-tight element such as a bladder separating the two. The bladder is charged through a gas valve at the top of the accumulator, while a poppet valve at the bottom prevents the bladder from extruding into the pressure line. The poppet valve is sized so that the maximum volumetric flow cannot be exceeded. To operate, The bladder is pre-charged with nitrogen to a pressure specified by the manufacturer according to the operating conditions. When the system pressure exceeds the gas pre-charge pressure, the poppet valve opens and hydraulic fluid enters the accumulator. The change in gas volume in the bladder determines the usable volume or useful fluid capacity. Now that our accumulator is charged with stored energy, watch it discharge and use the stored energy to accomplish work. In this learning, there are two types of pressure switches, the board-on tube switch and the piston switch, shown here. This pressure switch consists of a micro switch, a spring, a mechanical stop, a push rod, and a piston actuator. External lights are often used to indicate that the switch has been activated. When pressure builds in the system, it enters the device applying force to the piston actuator. This energy is transferred to the mechanical stop, compressing the spring, driving the push rod up until it activates the micro switch. Pressure switches are used to open or close an electrical circuit when a predetermined pressure has been reached. The purpose of a flow meter is to measure flow. It is not bidirectional and acts as a check valve blocking flow in the reverse direction. The main components consist of a metering cone, a magnetic piston, which is held in the no-flow position by a tempered spring. Fluid first enters the device, flowing around the metering cone, putting pressure on the magnetic piston and spring. As flow increases in the system, the magnetic piston begins to compress the spring, indicating the flow rate on the graduated scale. As the number of connections in a hydraulic system increase, so does the possibility of leaky fittings. Hydraulic manifolds drastically reduce the number of external connections required. Manifolds used for modular valve stacking incorporate a common pressure and return port. With individual A and B work ports for each valve station. At each station, additional control valving may be added by sandwiching or stacking the valves vertically. This is accomplished without any external connections. Manifolds are specified according to system pressure, total flow, number of workstations, valve size or pattern.
Fluid conductors are those parts of the system that are used to carry fluid to all the various components in the hydraulic circuit. These types of conductors include hydraulic hose, steel tubing, and steel pipe. This course will help you understand the benefits of these different conductors and where they are best used in a hydraulic system.
Transmitting power from one location to another is a key element in system design and performance. Fluid conductors describe the different types of conducting lines that carry hydraulic fluid between components. The three principal types of plumbing materials used in hydraulic systems are steel pipes, steel tubing, and flexible hose. A safety factor of 4:1 is recommended on the pressure rating of the plumbing material. To determine the working pressure of the conductor, we must take the rated burst pressure and divide by the safety factor of 4. Hydraulic hoses are used in applications where lines must flex or bend. In considering the use of hoses, one must first look at system pressure, pressure pulses, velocity, fluid compatibility, and environmental conditions. Hose construction has been standardized by the Society of Automotive Engineers. As an example, 100R2 or 100R4. This designation describes the cover, construction, pressure rating, and application. Hoses are usually pressure rated with a safety factor of 4:1. Different types and amounts of reinforcement give the hose specific pressure ratings. The reinforcement may be a natural or synthetic fiber or metal wire. The reinforcement may be braided or spiral bound. Required hose size depends on the volume and velocity of the fluid flow. Unlike pipe and tubing, hose sizes are designated by ID or inside diameter. Sizes are designated in 1/16 of an inch by using a dash and a number, equivalent to the numerator of the fraction. Example is -8 or 8/16 or ½ ID. Hose life is good, but all rubber slowly deteriorates with contact from various substances such as solvents, water, sunlight, heat, etc. Hoses are not as permanent as metal conductors and should be replaced every few years. Proper hose installation is critical. Improper bends, twisting, or lack of proper anchoring may lead to hose failure. Steel pipe is often a preferred conductor from the standard point of performance and cost. However, it is often difficult to assemble because welding is required to give maximum leak protection. It also requires costly flushing to ensure a contaminant-free system at startup. Pipe is specified by its nominal outside diameter, but its actual flow capacity is determined by its inside area. For example, schedules 40, 80, and 160 and double extra have the same outside diameter, OD, and can be threaded by the same pipe die. The difference is the inside diameter, ID, and area. Schedule 40 pipe is standard and has the thinnest wall, with more flow area, but less pressure rating. Tubing is used as a conductor when rigid lines are required. It is often easier to assemble and form, and requires no welding to achieve leak-free connections. As with all types of conductors, certain requirements must be met. The line must be large enough to carry the required flow and strong enough to withstand internal pressures. Tubing is measured and specified by its wall thickness and OD outside diameter. Pressure ratings are based on tubing grade and wall thickness. One piece of tubing is joined to another tube connector or component with a tube connector and fastening nut. Often the tube is pre-flared to 37 degrees to accept a 37-degree flare connector.
When hydraulic systems are designed, whether on paper or computer, the layout of the system is expressed in what is called a schematic. A schematic is a line drawing made up of a series of symbols and connections that represent the actual components in a hydraulic system. In this course, you will learn to identify basic schematic symbols. You'll also learn where they are placed in the schematic of a basic hydraulic system. Although there are dozens of different symbols used in a complex schematic drawing, it is important to be able to recognize several basic symbols.
Symbols are critical for technical communication. They are not dependent on any specific language, being international in scope and character. Hydraulic graphic symbols emphasize the function and methods of operation of components. These symbols can be rather simple to draw if we understand their logic and the elementary forms used in symbol design. The elementary forms of symbols are circles, squares, triangles, arcs, arrows, dots, and crosses. Click on each of the following categories to see how these common hydraulic graphic symbols are logically constructed, giving symbolic representation of its component. Lines. Understanding graphic line symbols is critical to proper interpretation of schematics.
Continuous lines indicate a working line, pilot supply, return, or electrical line. A dashed line indicates a pilot, drain, purge, or bleed line. Flexible lines indicate a hose, usually connected to a moving part.
Lines crossing may use loops at crossovers or be straight across. Lines joining may use a dot at the junction or at right angles. Reservoirs. Reservoirs that are vented are shown as a rectangle with the top line omitted.
Pressurized reservoirs are shown as a capsule.
Reservoirs may have fluid lines terminating above or below the fluid level. The above oil level return line terminates at or slightly below the upright legs of the tank symbol. The below oil line return line touches the bottom of the tank symbol. A simplified symbol to represent the reservoir minimizes the need to draw a number of lines returning to the reservoir. A number of these in the same circuit will represent a common reservoir. These symbols have the same function as the ground symbol in electric circuits.
Rotary devices are shown as a circle. Pumps having an energy triangle pointing to the outside perimeter indicate the energy is leaving the component. A sloping arrow through the circle indicates that the pump is variable or the output flow can be regulated without changing shaft speed. A control symbol with an energy triangle that is connected to an adjustable spring indicates that the pump is pressure compensated. Some types of pumps have internal leakage that is returned to the tank by a case drain. This is indicated with a drain line drawn leaving the circle. Pumps that are bidirectional are shown with two energy flow triangles. The symbol for a flow control valve begins with an upper and lower arc. This would symbolize a fixed orifice. An arrow drawn sloping through the arcs indicate that the orifice is adjustable. This would be the graphic symbol for a needle valve. When we add an arrow to the flow line inside a control box, we have indicated that the valve is pressure compensated or true flow control. A flow control valve with a check valve indicates reverse flow around the valve.
Directional control valves. The symbol for a directional control valve have multiple envelopes showing the number of positions the valve may have. A 3-position directional control valve is shown with 3 envelopes. Arrows in each envelope indicate the possible direction of flow while the valve is in that position. The center position in a 3-position directional control valve is designed according to the type of circuit or application. This centered position indicates the flow path of the fluid while the valve is centered. While there are many types of center configurations, the 4 most common are tandem, closed, float, and open. To shift the valve or activate it, we can use a mechanical handle or lever, an electric solenoid, or hydraulic pilot pressure. The springs indicate that the valve is centered when not activated. In position 1 or centered, fluid flows from the pump through the valve to the tank. This is a tandem center. When we shift the valve to position 2, fluid now flows from P to A, extending the cylinder, shifting to position 3, which shows flow now from P to B, and from A to T the cylinder retracts. Pressure valves. The symbol for a pressure valve begins with a single envelope. The arrow in the envelope depicts the direction of flow through the valve. The ports are indicated as 1 and 2 or primary and secondary. Flow through the valve is from the primary to the secondary port. Notice that in the normal position, the arrow is not aligned with the ports. This indicates that the valve is normally closed. All pressure valves are normally closed with the exception of a pressure-reducing valve, which is normally open. The spring located perpendicular to the arrow indicates that the spring force holds the valve closed. An arrow diagonally through the spring indicates that the spring force is adjustable. Pilot pressure opposes spring force. This is indicated by the dotted line running from the primary port perpendicular to the arrow opposite the spring. When the hydraulic pressure piloted from the primary port exceeds the force of the spring, the valve moves to the open position aligning the primary and secondary ports. Check valves. Check valve symbols are drawn with a small circle inside an open triangle. Free flow is opposite the direction the triangle is pointed. As the circle moves into the triangle, the flow is blocked or checked. Check valves may be piloted to open or to close. Pilot to open is indicated with a pilot line directed to the triangle shown to push the circle away from the seal. Pilot to close is indicated by directing the pilot line to back of the circle or into the seat. Motors. Hydraulic motor graphic symbols are opposite of hydraulic pumps. Their difference being the energy triangle points into the circle indicating fluid energy entering.
Two energy triangles pointing in indicate a bidirectional or reversible motor.
As with pumps, many hydraulic motor designs have internal leakage. A dotted line leaving the circle indicates a drain line to the tank. Cylinders. Fluid power cylinders with no unusual relationship between the bore and rod size are shown. Single acting, double acting, and double rod. An integral rectangle adjacent to the symbol for the piston indicates a cushion device at the end of the stroke. If the diameter of the rod is larger than usual for the bore size, the symbol must reflect this. Filters. The graphic symbol for a hydraulic fluid condition device is shown with a square standing on end. A dotted line across opposite corners indicates that it is a filter or strainer. Adding a check valve across and parallel to the ports indicate that the filter has a bypass. Heat exchanger. Hydraulic heat exchangers may be considered coolers or heaters. Their graphic symbols are often confused. As with a filter, the base symbol is shown as a square on end. Arrows pointing in indicate the introduction of heat or a heater. Arrows pointing out indicate heat dissipating or a cooler. Arrows pointing in and out would indicate a temperature controller or temperature that is maintained between two predetermined limits. In this learning lab, you will learn the proper name. A schematic is a compilation of graphic symbols interconnected, showing a sequence of operational flow. In short, they explain how a circuit functions. Correct schematic reading is the most important element of hydraulic troubleshooting. Although initially most circuits may appear complicated, recognizing standard symbols and systematic flow tracing simplifies the process. This circuit uses two sequence valves. They are normally closed valves that open at a predetermined setting. By tracing the flow in this circuit, we should be able to determine how this circuit is designed to operate. This process is called reading a schematic. Let's begin at the pump. Follow the flow past the relief valve to the directional control valve, which is shifted to the upper position as shown. The directional control valve directs flow to the lines in the upper circuit. Here, flow can go three places. The upper check valve blocks one passage. The closed sequence valve blocks another. But flow to the A port of the actuator is open. As the cylinder rod retracts, flow from the B port is blocked at the check valve, so it exits to the tank through the directional control valve. When the cylinder is fully retracted, pressure will build in the pilot passage of the sequence valve. It opens and sends pilot pressure to the directional control valve. Pilot pressure on the upper side of the directional control valve will shift the valve downward. Pump flow is now directed to the lower circuit, and the flow here goes to three places. It is blocked at the check valve and blocked at the closed sequence valve. But flow to the B port of the actuator is open. Flow in the port will apply pressure to the piston and extend the cylinder. Flow out of the A port is blocked by the upper check valve, so it flows through the directional control valve to the tank. When the cylinder is fully extended, pressure continues to build. Pilot pressure opens the sequence valve on the bottom. This sends pilot pressure to the lower side of the directional control valve, shifting it back into the upper position. Now, pump flow is once again directed to the rod side of the actuator to retract the cylinder, and the cycle begins once again. Tracing the flow in this circuit reveals that it is designed to keep retracting and extending automatically. Now that we understand the circuit, we may conclude that the proper function of the system will depend on the proper setting and function of the sequence valves, and the proper function of the hydraulically piloted directional control valve. This is a high-low circuit. Such a circuit would be used to achieve high speed or rapid advance at low pressure, followed by slow speed and high force. A good example of a high-low system would be a press, where the ram would rapidly advance up to the workpiece. At that time, the pressure starts to build. The flow from the high-volume pump is diverted to the tank. The low-volume pump would produce the little flow needed to continue moving the ram into the workpiece. The pressure will continue to rise until it reaches the relief valve setting. When the directional control valve is reversed, the pressure drops and the unloading valve closes. The cylinder would retract at a rapid speed. Now let's examine more closely the components that make up this system. First, the unloading valve. This valve has been set at 500 psi. When the system pressure reaches 500 psi, this valve will open and allow the flow from the high-volume pump to go back to the tank at minimal pressure. Next, we will look at the function of the check valve. When the system pressure is less than the unloading valve setting, flow from the high-volume pump flows through the check valve to combine with the flow from the low-volume pump. After the unloading valve opens, this check valve closes so that the flow from the low-volume pump won't flow to the unloading valve. Now, let's take a look at the high-low pump group. This is a double pump. These pumps have a common inlet and separate outlets. During low-pressure rapid advance, both pump flows are combined. When the unloading valve opens, the large pump's flow returns to the tank, and the small pump's flow is used to do the work. Finally, we will look at the system pressure relief valve. This valve limits the maximum system pressure. Notice the schematic shows the pressure at which the valve should be set. Now, watch as these components work. In our circuit, the cylinder has a weight that would cause it to free fall or drop at an uncontrolled rate. A counterbalance valve is placed in the rod end port of the cylinder to apply back pressure. The back pressure is the result of the load trying to force the fluid out of the cylinder and through the counterbalance valve, which is closed. The counterbalance valve has to be set slightly above the load-induced pressure. When shifted, the directional control valve applies pressure on the cylinder piston. This, in turn, increases the back pressure, causing the counterbalance valve to open, allowing the cylinder to lower the load at a controlled rate. Now let's examine more closely the components that make up this system. First, we'll look at the offline or kidney loop filter circuit. This circuit consists of a pump motor group, a filter, and an air-to-oil heat exchanger. The pump draws hydraulic fluid from the reservoir, passing the fluid through a filter and an air-to-oil heat exchanger. This circuit usually runs continually to keep the hydraulic fluid clean and cool. Next is the pressure-compensated pump. The pressure-compensated pump de-strokes when the directional control valve is centered. At this time, there is pressure being maintained between the pump and directional control valve, but no flow. When the directional control valve is shifted, the pump goes on stroke, providing flow for the circuit. Next, we have the directional control valve. This is a 3-position 4-way valve with a float center. This valve, when centered, will block flow from the pump so that pressure will build and de-stroke the pump. Both work ports are routed back to the tank, so there is no pressure in the work port lines, except between the rod end of the cylinder and the counterbalance valve. Now, we look at the counterbalance valve. The counterbalance valve maintains back pressure on the rod side of the cylinder so that the cylinder brings the load down at a controlled rate of speed. The check valve is used to lock and hold the load on this cylinder when the directional control valve is centered. Now, let's watch the system work again and see how each component operates.
Before you begin this section, you should already be comfortable with the previous section, Understanding Schematics. This basic system design section builds on your knowledge of symbols and schematics by showing you how to identify actual system components as they are displayed on the screen. You will notice that whenever a component is displayed, that its associated symbol is also shown. The second part of this section will teach you how to build a hydraulic system using realistic drawings of components rather than using symbols. These exercises will give you a feel for how actual systems look and operate.
In previous sections, we have discussed hydraulic components individually, showing their function and application. In this section, we will show an actual working system, highlighting some of the components previously studied. Click on View 1, View 2, View 3, or View 4. Choose an area of interest and click on the appropriate number.
Fan-cooled heat exchanger, connected in series to the offline recirculation loop, provides cooling for the main hydraulic reservoir. System temperature must not exceed 71 degrees Celsius. Offline recirculation pump and motor, 3 kilowatt electric motor, 50 liters per minute gear type hydraulic pump, provides flow for the recirculation loop. Offline recirculation filter, connected in series to the offline recirculation loop. 10 micron pressure filter. Spin-off housing. Offline filtration. System pressure line filter, connected in-line and downstream from the main hydraulic pumps. 10 micron filter. Provides filtration protection for a proportional valve on the motor drive manifold. Flow meter, installed in the main pump case drain lines. 0 to 40 liters per minute monitoring. Provides monitoring of the case drain flow to determine internal wear. The case flow must not exceed 20 liters per minute. Shutoff valve and pump suction line, installed between the pump reservoir and suction port. Swing valve design with locking handle. Closes reservoir flow during pump changeout. Main pump, 180 liters per minute at 1750 RPM. Axial piston pressure compensated. Provides system flow. Compensator set at 100 bar.
Choose an area of interest and click on the appropriate number.
System accumulators. 20-liter accumulator pre-charged to 30 bar. 40-liter accumulator pre-charged to 30 bar. Provides stored energy in the event of input power loss. Accumulator bleed-off and isolation valves. Ball valve design, normally closed. Used to bleed down and isolate accumulators for maintenance or repair. System reservoir, 200-liter reservoir, provides oil storage for main system power unit. Reservoir breather, 5 micron, spin-on element, provides filtration protection for vented system reservoir. System pressure gauge, 0 to 200 bar, glycerin filled. Used to measure main system pressure relief and pump compensators. System return line filter, 10 micron element, bolted cover for element removal. Provides main source of contamination control for hydraulic systems. Reservoir cleanout cover. Provides access to clean out the reservoir. Bolted with Buniseal. Level indicator. Sight glass designed with thermometer. Provides a visual indication of fluid level. Do not fill reservoir past top glass.
Choose an area of interest and click on the appropriate number.
Manifold assembly. Ductile iron. 400 bar rated. Multi-valve 4-station valve stack. Pilot valve, size 6 directional control valve. Float center. Shift size 25 directional control valve. Flow control valve, size 6 sandwiched configured. Controls shift speed of size 25 directional control valve. Directional control valve, size 25. Starts, stops, and changes direction of flow to hydraulic cylinder. Check valve, pilot operated. Locks cylinder in position. Pilot valve, size 6 directional control. Pilot opens check valve. Pilot valve, size 6 pressure reducing valve. Pilot control for size 16 pressure reducing valve.